this 3D visualization of a heavily saturated home layout. It shows exactly what happens when consumer-friendly hardware meets enterprise-grade demands. Because the eero app makes it effortless to add new hardware, advanced users often make a critical error. In an attempt to maximize their coverage, they oversaturate their environment with too many nodes. In a highly dense deployment, relying entirely on wireless communication carries severe performance consequences. Nodes placed too closely together compete for the same radio frequencies, creating an environment of self-inflicted signal interference. The eero app actually captures the diagnostic telemetry needed to identify this interference. Yet most users ignore these metrics and leave the advanced software configurations at their factory defaults. Optimizing a mesh network requires stripping away the plug-and-play marketing and instead manipulating both the physical environment and the underlying logical parameters of the network. Mastering eero's architectural mechanics is the only reliable way to guarantee multi-gigabit throughput and sub-20 millisecond latency. The first step in building a stable mesh requires solving the physics of radio frequency, or RF, attenuation. Every material inside a residential structure degrades the integrity of a wireless signal. This diagram demonstrates how a 5 GHz waveform interacts with different construction materials. The signal passes cleanly through low attenuation materials like drywall, but the wave scatters and loses its strength immediately upon hitting a cross-section of brick. Now watch the same waveform strike a highly dense object, like a metal HVAC system. The signal reflects entirely, casting a dead zone directly behind the object, known as an RF shadow. This dictates the first rule of physical optimization. You should never place a satellite node directly inside one of these RF shadows or dead zones. The correct strategy is to position your satellite nodes exactly halfway between the main gateway and the dead zone you are trying to illuminate. By placing the hardware at this midway point, the node secures a high signal-to-noise ratio for its connection back to the main router, giving it the necessary bandwidth to push into the weak area. When translating this to multi-floor deployments, a common error is stacking nodes in a straight vertical line, which forces the signal to punch directly through dense flooring materials and joists. This architectural layout illustrates the correct approach for a multi-story home, arranging the nodes in a triangulated, staggered pattern. Triangulation ensures the vertical coverage zones propagate through open-air spaces, like stairwells or open-concept living rooms, rather than fighting through solid barriers. Precise physical placement establishes a clean foundation for the hardware. Without this, no amount of software routing can function efficiently. With the physical placement secured, the network relies on a specific invisible communication channel called the backhaul for the nodes to talk to each other. This diagram reveals the structural flaw inherent to default wireless backhaul. The access point is forced to use the exact same radio to both receive data from the main gateway and transmit data to a laptop client, rapidly toggling back and forth. This toggling effectively halves the available airtime. As the data bottlenecks, the latency counter ticks up, adding 5 to 20 milliseconds of delay for every hop across the network. The single highest impact physical optimization you can execute is establishing a wired Ethernet backhaul. Connecting your nodes with a physical Cat6 cable reconfigures the eero's internal radios. Here, a physical Ethernet line handles the connection between the gateway and the node. This reclaims 100% of the 5 and 6 GHz spectrum exclusively for client devices, allowing the node to emit a constant, uninterrupted wave. Moving this internode traffic to a wire drops the latency to less than 1 millisecond. A wired connection also completely isolates the backhaul traffic from environmental RF interference, thick walls, and competing Wi-Fi networks. Reconfiguring the mesh with physical backhaul ensures the individual nodes stop functioning as signal repeaters and instead operate as an enterprise-grade distributed switch. At the software level, eero uses a dynamic, self-healing routing protocol called TrueMesh rather than relying on a basic static routing table. Since the eero OS version 6.14.0 update, this algorithm actively evaluates both the strength of the node-to-node links and the specific telemetry between the node and individual client devices. This dual evaluation allows the system to calculate the optimal data path in real time, factoring in current airtime availability and packet loss rates across every possible route. To fully leverage this telemetry, navigate to the Advanced Settings menu and locate the Client Steering toggle. Ensure this is active. Client steering utilizes the IEEE 802.11v standard, also known as BSS Transition Management, to proactively manage client connections. The network uses this protocol to evaluate capable devices and suggest that they transition to a faster 5 or 6 GHz band when bandwidth is available. It also monitors for devices stubbornly clinging to a weak signal from a distant access point and forces them to jump to a closer, less congested node. This pairs with adjacent IEEE standards to execute roaming handoffs in under 50 milliseconds. Client steering prevents roaming loops and dropped voice-over IP calls by taking routing decisions away from the individual client device and handing them to the intelligent mesh algorithm. The final configuration requires accessing the deepest layer of logical settings found within the Network Services menu. First is Smart Queue Management, or SQM, which fixes the specific issue of buffer bloat. In this data pipeline diagram, high-demand tasks like a 4K download are represented by large, bulky data blocks. They are choking the flow of the small, fast packets required to maintain a real-time voice-over IP call. Activating SQM reorganizes the traffic. It allocates a dedicated, unimpeded lane so the small, latency-sensitive packets can bypass the large download blocks without delay. Next is local DNS caching, a default feature originally intended to speed up URL resolution. In reality, holding on to outdated network-level DNS records often causes endless load screens and routing loops for advanced users. Disabling local DNS caching forces the network to fetch fresh records, immediately resolving these pervasive, hard-to-diagnose connectivity glitches. Finally, enabling WPA3 ensures modern encryption protocols are strictly enforced, which is particularly critical for devices operating on the 6 GHz band. Manipulating these specific logical parameters eliminates the invisible bottlenecks that silently throttle high-speed internet plans. The result of these adjustments is an optimized network fabric that replaces the oversaturated consumer setup. This requires triangulated, staggered node placement to avoid physical RF attenuation. It demands a wired Ethernet backhaul to reclaim the entire wireless spectrum for client devices. And it relies on client steering and smart queue management to orchestrate logical data flow, eliminating roaming loops and latency. When you view the final integrated system, glowing data pulses travel flawlessly from mobile devices through wired nodes, dodging structural obstacles without collision. By combining precise architecture with advanced tuning, the hardware operates as a flawless, invisible utility.